So as I said at the beginning, we work on the fundamentals, but the two technologies that motivate us is corrosion, so degradation, and the latter is electrochemical energy conversion based on high temperature fuel and electrolysis cells. So they sound like different applications, but in both cases we deal with the same type of physical properties, the same type of materials. So oxides that transfer charge, that transport ions through them, that contribute to either the degradation or the efficiency of electrochemical devices. So this latter, electrochemical energy conversion devices like fuel cells or electrolysis cells, can couple to high temperature sources like nuclear reactors to provide them the heat necessary, say, to electrolyze steam and generate hydrogen or hydrogen-based hydrocarbon fuels. And the nuclear energy field is interested in that application because we see it as one means to expand the applicability of nuclear energy beyond electricity, but also to making fuels that is good for transportation. If this type of device, like a reversible fuel and electrolysis cell, could couple to a nuclear plant, it can make the operation of a nuclear plant more flexible. So currently in the US, all the nuclear plants run with what we call a base load, so they cannot follow the fluctuations in the electricity demand. They run at the base of the load curve. Okay? But if you couple such a device that is able to generate electricity and fuels can serve to store electricity and convert that again to electricity along with the electricity from the nuclear plant directly to actually address the peaking behavior in the electricity demand curve also. These two technologies or technological application areas are what I have mainly worked on, but recently I have been developing interest also in information storage and processing devices that also rely on the same processes as we study in corrosion or in high temperature fuel cells. So these are oxide materials which undergo redox reactions, and as they do, they change their resistant state, so how resistant they are to electricity flow, which enable one to register information. So high resistance versus low resistance, passing current through it or not current through it. So this would be considered as the next generation of very fast and non-volatile memory devices. And fundamentally, exchange of oxygen that we study on corrosion or on fuel cells is exactly taking place on these materials too, or transport of charges like oxygen defects or electrons or holes are also going through these materials. And even the type of materials that we study for corrosion for fuel cells is again very similar to those that are being considered for these next generation memory devices. So I see implications of the knowledge that we have been developing also in enabling the progress in that new technology.